So with NMR, we're looking at nuclei, and very particular nuclei have a magnetic moment associated with them. And there's only certain nuclei that do this. For our sakes, the nuclei that are going to become important would be the hydrogen nucleus and then our carbon nucleus. It's going to be a standard hydrogen, so hydrogen with the atomic mass of 1, and then for carbon, anybody know the isotope that works for carbon? It's carbon 13. What's the most common isotope for carbon? 12. Which is why carbon 13 experimentally takes a lot longer, because we're detecting a very small amount of carbon within an individual sample. Okay? So those two particular isotopes are the most relevant for us. There's all sorts of other isotopes that also work, and depending on what you're trying to do, you may look at those individual structures. So what's happening is that these nuclei have a magnetic ability associated with them. So what we can do is look at how they're going to align with an external magnetic field. Right? And in that aligning process, we can then also go through and tweak them. So we can excite them or change their energy states a little bit, and we can actually watch the time it takes for that entire sample to get back to kind of its steady state. Okay? So that roughly approximates what's happening within the magnet. With these experiments, because we're looking at magnets and how they interact with a magnetic field or an external magnetic field, there's all sorts of other things that can contribute to it. Like, are there electrons hiding the nucleus? If electrons are hiding the nucleus, it's going to change the amount of energy it takes for us to go through and excite or change its energy state. We can detect that difference, and that's how we can end up using NMR to relate back to structure. Okay, so it's kind of fun in that respect. And that's our hydrogens, or our electrons hiding or shielding the nuclei. Just like with any magnet, if you bring one magnet near another magnet, they start to interact with each other. Okay, so one of the other things that we'll find, particularly with hydrogen NMR, is that if we have multiple hydrogens near each other, they can interact with each other as well as with the magnetic field, as well as with their local environment. Okay, and that's what contributes to our splitting patterns. So it's ultimately all coming back to this: hydrogen's a magnet, how does it interact with other magnets? Okay. Within the spectrometer, they're giant magnets. You drop your sample inside it, we can hit it with radio frequencies, and it outputs this information that then gets mathematically interpolated or interpreted into a signal that we can then evaluate, and that's what we have to then process. Okay. So before we get back into the actual spectra itself, we should look at some experimental considerations. When we look at the actual signal, what we're looking at is these hydrogens either being shielded or de-shielded. So it's looking at the electron clouds around them. If there's a lot of electron density around an individual nucleus, it's now shielded from the magnet. If we've removed that electron density, it's now de-shielded. Well, it's more or less shielded than what? That's ultimately what's causing our shift, is that shielding. But what is it shifting from?
Zero.
What's zero?
TMS.
Okay. Zero is something that we actually have to put in and tell the instrument, this molecule is zero. Compare everything to this signal. Otherwise, we don't get chemical shifts. We don't get any numbers associated with anything. We just see a spectra with a bunch of lines on it, and we have to assume some kind of external information. Okay, so what we will always end up doing is putting in a standard. That standard is TMS, tetramethylsilane. Okay, it's always put into your, or nearly always put in, and it's defined as your zero signal. The other thing that might show up, I don't remember, is that on this slide? The only other thing that might show up would be a secondary solvent. Okay, for our NMR magnets to actually work pretty well, our molecule has to be able to tumble and move. If it can't move, then what ends up happening is certain hydrogens are going to look different than other hydrogens, okay, depending on what's happening within the sample. Okay, so we always want our molecules to be freely moving. To do that, we have to add a solvent. There's a variety of solvents that we can use. Chloroform works. Dimethyl sulfoxide also work. The issue with a lot of solvents, though, particularly organic solvents, is what's also present in that solvent. carbon and hydrogen. If we use a solvent that has carbon or hydrogen in it, that solvent is going to show up in our spectrum. If it shows up in the spectrum, it has the ability to effectively wipe out any other signals. So one of the things that we'll do with hydrogen NMR is we will change the structure. We will remove the hydrogen, but we have to replace it with something similar as far as size and chemistry goes, but not have that magnetic moment. So what we end up exchanging it for is deuterium. So when we're looking at organic solvents used in our experiments, we're using any kind of deuterated solvent, meaning all of the hydrogens have been replaced with deuterium. The only difference, deuterium has an extra neutron. That extra neutron disrupts the magnetic moment of deuterium, and we no longer see it in the NMR. Okay, so it's a nice little simplification for us. And then our organic protons, all of the extra hydrogens within our sample will absorb somewhere to the left in our spectrum of TMS. Okay, and that's because for some reason we decided to do an inversion in our chemical shift scale. So what we're looking at is that 0 to 14 range for HNMR. That's known as downfield of our TMS. Okay, so this downfield and upfield thing and shielding versus deshielding can get a bit tedious to deal with and manipulate. Realize that in most circumstances you can get away with just looking at the numbers. Okay, bigger numbers means downfield. Oh, shoot. Well, here's the discussion on our solvent. We have to have our molecules freely tumble and move. The classic example for why would be if we looked at everybody's favorite chair, cyclohexanes. What's the difference between these hydrogens? Are they chemically the same? No, one's axial and one's equatorial. Okay, so if we looked at this particular chair, we're going to end up seeing different signals for those hydrogens. Okay? However, in most environments with this chair, what happens? It can do a chair flip, exchanging the hydrogen from the axial to the equatorial position and vice versa. So we end up kind of washing out that difference in our hydrogens. So our molecules need to be able to constantly move and rotate so that we can remove that extra interpretation. Same idea applied even more kind of dramatically. If we looked at this structure, and let's say CH3, how many hydrogens are in that compound? Okay, how many signals do we see? We see 2 signals because these 3 hydrogens come out chemically the same. What happens if we look at this structure? Make sure I'm drawing this right. What's the relationship between these 2 drawings? They're the same. They're identical. The magnet, however, is going to start to interpret these things differently, because if we try to directly superimpose these, can we directly superimpose them? Only if we can rotate it. What if rotation is prevented? Then they start to become different. Okay? That difference is something that the magnet could detect, and that's very problematic, which is why when we set up our samples, we want to make sure that they can freely rotate and move so that we can wash out this difference, okay, which ultimately isn't a difference. So if we go through and look at solids, what happens with a solid? Would we be able to test a solid? No, it doesn't move, right? So we don't have that motion. So how do we go through and test those? That's where we dissolve it in our secondary solvent, and that's where we get our chloroform or our dimethyl sulfoxide. And again, the problem, both of those have hydrogens. Particularly in the hydrogen NMR, we would have such a vast concentration of the solvent in there that it would wipe out any signal that we could get from our molecules. And so what we have to do is change those compounds to deuterated solvents, remove the hydrogen and exchange it with the deuterium. In that case, we no longer have a hydrogen, so what signal would we expect in our NMR? There's no hydrogen. There shouldn't be a signal. Turns out we do end up seeing a signal show up in the NMR spectrum, and it kind of depends on the quality of the data that you're actually analyzing, if you're getting computer-generated data or real data. If it's real data, you will see a peak. Okay? And the reason being is that that deuterium can come off of the structure and exchange with normal hydrogens, okay, or light hydrogens. Those lighter hydrogens now make it onto the structure, and we see some concentration for the chloroform. Okay? So if you happen to run NMR and you use a really old sample of deuterated chloroform, you probably expect a really big peak for the chloroform in your HNMR because it's been open and it's been exposed to normal hydrogen. Okay? So we do tend to see those signals pop up. Most of the time in the data that you're looking at, you probably haven't seen chloroform show up. Why? We're removing it for you, so you don't have to interpret it. If you look at the spect_all file, A, B, and C, the last three unknowns, all of them have chloroform in them. Okay, so you can see that. To make those even more complicated, they also all have, to varying extents, other impurities, like water, okay, which makes it a lot more difficult to interpret your NMR because you now look at a signal that doesn't belong in the compound. Okay? It can also show up in carbon NMR, and in carbon NMR it shows up at about 77.2, but we see it show up as a triplet, so 3 peaks right on top of each other, are really, really close to each other. If you see those signals, you can ignore them. They aren't important to evaluate because they're part of the solvent, not part of your compound. Okay? Most typically, you'll see chloroform show up. Very rarely does TMS directly show up in your samples. That said, the ACS exam seems to like to put in a nice big peak for your TMS. Where would we expect to see the signal for TMS? At 0. So if you see a peak at 0, is that part of your sample?
No.
No, that's there to define 0, leave it out. You don't have to worry about interpreting it. Okay? The number of signals. So this is where we can start to bring in our interpretation. I kind of wanted to go through some more of the complex examples with the number of signals that you would see and then also the multiplicity. Other than that, that rest of that information about your integration, your standard chemical shifts, all of that is in the already posted online lecture. Okay. When trying to determine the number of signals, realize that in hydrogen NMR, every single hydrogen is counted. Okay. Whether it's unique or it's similar to something else, every single one gets counted. Okay. What ends up happening, though, is that if it's similar to something else, what's their chemical shift? The same. So they both show up at the exact same point. Well, if they both show up at the exact same point, we can't tell a difference between them and we see one signal. Okay, and that's ultimately what's happening within our HNMR. How do you identify whether it's the same or different? That goes back to kind of the chirality argument and trying to determine how those structures or those atoms overlap or are related to each other. Okay? In general, the way that I like to think about it is if we take our molecule and I point to a hydrogen and it gets spin, flipped, rotated, tossed on its head, and then I open my eyes, can I point to the exact same hydrogen? If I can, then it is unique. If I can't, then it's similar to something else, and whatever it's similar to, right, those are now grouped as one chemical type. Okay, and I see one signal for them. You can see some subclassifications come out of this. So if you look to the textbook, they can refer to some of these as enantiotopic and diastereotopic. I don't remember if I left those questions in on Sapling or not. Okay, so watch out for that when you go through and do the online homework. Enantiotopic hydrogens will end up with the same signal, okay, because just like enantiomers, we get very similar properties. Okay, so we get the same chemical shift. Diastereotopic hydrogens generate different signals, so they show up with different chemical shifts. So if we take a look at the molecule shown below, Can you guys name this one yet? Looking at 2-chlorobutane, so we got those 4 carbons. In the case of HNMR, we probably want to go in and draw in our hydrogens. Let's not pick blue, let's go with black so it stands out. Everybody see those on both screens? How many hydrogens are in this compound? Total. Should have 9, 3, 6. I don't know why I'm saying 3, 6, 9, but there's 9 hydrogens. How many signals would we expect to see? Okay, this is where this one becomes tricky. So let's go as simple as possible first. This CH3. Right, let's pick. I can go ahead and color them out now. Take a look at that red hydrogen. Would I be able to distinguish it from any other hydrogens? I can distinguish it from some, but not all. Would I be able to distinguish it between that now red hydrogen? No. So those are going to be chemically the same. We'd expect one signal for them. How about this hydrogen? That red hydrogen now. Still no. So we still see one signal. What happens with our blue hydrogen? Is it different than our red hydrogen?
Yes.
Yeah. Okay. What we're looking at is the atom it's bound to, and yes, we do see a distinct difference there. Okay. And now I'm going to do the complete flip. How about the orange hydrogen now on the far right? Is it different from the red one? It is different from the red one. Why is it different from the red one? We moved that one atom away. Can we tell a difference when we move that one atom away? Yeah. In the case of our orange hydrogen, we're bound to a CH2. In the case of our red hydrogens, we're then bound to a carbon with a chlorine attached to it. Okay, so we can tell a difference between our red and our orange. Can we tell a difference now between those two orange? Nope. So they're going to get the exact same signal. The last guy there. So at this point, we now have 3 different types of hydrogens. Okay, minimally. So now let's go through with what I would argue is probably the most confusing part of this, or difficult part. Are they all different from the purple hydrogen? Okay, that one's a CH2, everything else is CH3s. So I would agree that those are going to be distinct. So we should expect at least 4 signals. What happens now with, I'm kind of out of colors, and I don't think green shows up very well. How about the green hydrogen? Can you guys see that? Green hydrogen. So we're looking at the hydrogen immediately next to our purple hydrogen. They're both bound to the exact same atom. Are they different from each other?
They're on different sides, right? One's coming at you, one's going on the side.
Doesn't matter if it's on a different side. One's on the side of the chlorine, the other one's on the side of the hydrogen. That means they see something very slightly different. If that difference is enough, their chemical shift becomes different. And what we end up seeing is instead of 4 signals, we see 5 signals. Okay? In general, this is fairly rare as far as a phenomenon goes. Why? When does this... So number one, it's a very small difference. It's very, very subtle. If our single bond can freely rotate enough, we can just say that those are close enough in similarity that we don't really see a difference, that those 2 signals show up maybe slightly different. Maybe our purple one has a chemical shift of, where are we? So let's say 2.10, and our green one has a chemical shift of 2.09. Yeah, they're different. Technically, they're different. But as far as our interpretation ability, they're going to fall effectively right on top of each other, and we are not going to see that difference in the NMR. Okay? For us to really pick up that difference, we have to see a drastic difference with our other atom, with our chlorine versus our hydrogen. Okay? So what are we eyeing right here? What is special about that carbon that is causing this difference? We're looking at a chiral carbon. If there is a chiral atom within your structure, the NMR becomes drastically more difficult to interpret. All right? If you look at the spect_all file, there are, I think, 2 or 3 really difficult ones that have to do with chiral atoms. Those chiral atoms make it much more difficult to interpret because we end up looking at a CH2 that when we look at the spectrum, they come out as CHs. And now it becomes a lot more difficult to interpret. Okay? Yes?
So that trend that you kind of drew, the purple shift versus the green shift, is that typically what happens if there's a hydrogen that's on the same side of the molecule as like a substituent?
As the chiral substituent. It changes the shift. Let's just be happy with changes the shift and not worry about quantifying it. Yes?
Should the chemical shift less than 2? Just an answer.
Deciding what the exact chemical shift was, you'll notice that I picked 2.1 and 2.09. Why did I pick those numbers? These are hydrogens bound to carbon, and it's an sp3 carbon to boot, which means we're looking at alkane-type hydrogens. Okay? Fairly valid, which means we would expect those signals to show up in the alkane-type region. Where's the alkane-type region for hydrogen NMR?
0 to 2.
0 to 2. Why did I put this just over that threshold? Because it's attached to a carbon that's attached to a chlorine. That electronegative element of the chlorine withdraws electron density, causing the CH2 to show up at a slightly larger frequency. Okay. Picking up the subtleties within the chemical shift ultimately is something you're going to be responsible for when it comes to the ACS exam, but in very small amounts. Okay? So what you want to evaluate is pretty much everything except chemical shift first, see if you can eliminate answers, and then if you have to, you can go back and put a lot more weight in interpreting the chemical shift. Much the same idea of IR. I don't expect you to go into the fingerprint region of the IR unless you have more information. That more information would have to be, here's 3 structures you're looking at. The only difference between them would show up in the fingerprint region. Yes, now you should go into the fingerprint region. But if you're just given an IR spectrum and said analyze it, you shouldn't touch the fingerprint region because you don't know anything that's going on in there. You don't have the extra information to interpret that. The only time you should interpret the chemical shift beyond those general ranges that are supplied in that spect_all file is if you've got some more information. You're now comparing between 2 structures, and the only difference between those 2 structures would fall in the chemical shift. That's when you can take advantage of that information. Other than that, get a quick superficial pass and move on. Okay? One extra piece of information that I'll tag on here. Chemical shift is a big thing to write out and say. I'll say it just because I think it's easier to say. But we tend to not want to write it out. So what do we supply instead of saying chemical shift or writing out chemical shift? You'll typically see a delta. You might see me specify it as a CS, okay, just to be lazy, but that delta symbol is also referring to your chemical shift. Okay? Questions about our chemical shifts and our number of signals? All right, since we've got the structure and it's all nicely colored, let's go through and piece some other information out of this. What would happen if we looked at the integration? How many red hydrogens are there? 3. What's the integration come out to? First pass, we'll say 3. Okay, you might see it written as a 3 underneath that signal in your chemical shift line, or you might see it written out as a 3H
Above, right?
directly next to it. You could potentially see that underneath, but typically if we add the H, it's written next to the signal up in the spectrum. Okay. How many blue hydrogens are there? So we could say that as a 1H. How many orange hydrogens? How many green? Got 1H. And how many purple? Got 1H. Those two, depending on what happens, might show up as a 2H, depending on how different the spectra decides to see it. Okay? And ultimately, or how different the magnet decides to see those two hydrogens. That detection ability has to do with how big the magnet is. The bigger the magnet, the more likely you'll see a difference between those. Okay? Because it can now detect those subtle differences. Does it have to be supplied as 3H, 1H, 3H, 2H?
No, it could be any ratio.
It can be any whole number ratio of that. That could very well have been 6, 2, 6, and since I'm back to black, 4. Okay? It's any whole number ratio. So be aware of that kind of complication when you go through and look at your integration. Okay? It does not have to be exactly that many hydrogens. What's a quick, easy way to find out if it is exactly that many hydrogens? Sort of quick, easy way. You could look at a formula. Okay? So if you're given the mass spec and you calculated out the molecular weight and a potential formula, if the hydrogens from your formula match the hydrogens in your reduced ratio, then you have the exact number of hydrogens. If it's double, then you need to double it. Okay? If it's some derivative thereof, then we got to be a little bit more careful because there could be something else going on within there. Could be some extra symmetry within the structure. Typically, you're going as multiples. Questions on the integration? Okay. And only because we've got this structure here, we're now going to introduce this next fun topic. We're going to look at the most difficult to look at, which is our multiplicity. What's happening with our multiplicity?
Number of peaks.
It's the number of peaks. Okay, so it's also referred to as splitting. I think number of peaks is going to be the best way to interpret it here. How do we determine our number of peaks? Neighbors plus 1 equals peaks. Okay, so it's the number of hydrogen neighbors plus 1 will equal their number of peaks. Why do we count the number of hydrogen neighbors?
They have an effect on the peak, right?
They're going to have an effect on the peak. So each of our signals is a magnet. If we bring another magnet near it, that magnet can either have an additive effect or a subtractive effect, for lack of a better description. Okay? That's going to get us two different types of signals. So the simplest example that we could go with, if we just had one hydrogen and we brought in, let me step back on that. We had one hydrogen. We have the option of it being aligned with the field up or potentially against the field down. Both of those are valid arrangements. Okay? If it's just that one hydrogen, what's the magnitude in both cases?
0, right?
One's positive, one's negative, but it's still going to be the exact same magnitude. So we get one signal because it's the same magnitude. What happens if we bring in a neighbor? That neighbor can now either align with it, or it could have aligned against it. So we've got all of those possible options. What's the difference in magnitude between our top or our left, those two? Let's just stick with that. One will be positive 2, one will be negative 2. I keep hitting that. Right. So our magnitude is the same for that. What happens in the case of the other one? They both cancel out, which is different from our first one. So how many signals do we expect? 2. One where we had an additive effect and one where we had a subtractive effect. What's the intensity of those two signals? So how many different possibilities contributed to each of those? Well, I had two possible states here, and I had two possible states there. What's the ratio in intensity between those? 1 to 1. So if I have one hydrogen neighbor, I expect two peaks, and those two peaks should be the exact same intensity. What happens if we bring in a third neighbor? All right, now we go through the exact same situation and check all the possible alignments and check all the possible magnitudes, and what we end up seeing is that we get 3 sets of possible signals. Right? Within those 3 sets, we get one extreme, we get a smaller extreme, that doesn't quite work. We'll get a ratio of 1 to 3 to 1. Let's just run that. So within our 3 sets, we'll end up with 2 sets that are equal in intensity and 1 set that is 3 times as much, has 3 times the possible states. Okay? So what we end up seeing in the case of 2 neighbors is 3 peaks, and we get a slightly different peak pattern. Ooh, don't do that. Sorry. So 1 neighbor gets us 2 peaks of equal intensity. 2 neighbors gets us 3 peaks. We end up with that kind of patterning. 3 neighbors, 4 peaks. And you'll notice that we always kind of maintain this symmetry. It must go up and it must come down. Okay, every single time. At no point will ever just go up and it never come back down. Okay, we have to get this symmetry associated with it. Those people that are really good at patterns, notice that that's where we're getting this n+1 rule for being our number of peaks. The intensity ratio comes from Pascal's triangle. I think I said that right. I think it's Pascal's triangle. All right? Who looked at how you could build triangular shapes by adding different sequences up to generate those shapes. That pyramid is shown in that Spectol file. Okay? So let's now take this information and start to interpret what we would expect for our multiplicity for this structure. So for our red hydrogens, how many neighbors do they have? They have 1 hydrogen neighbor, being that blue hydrogen. Okay, well, 1 neighbor plus 1 means 2 peaks. And what we see, 2 peaks of equal intensity, doubling. What defines a neighbor?
3 bonds.
It's within 3 bonds. In general, there are some approximations that we can run with this. You can move to the next atom and put a hydrogen. If you do that, you're at the 3rd bond. So let's count it out for our red hydrogens. We have 1, 2, 3 bonds, and we have stopped at a hydrogen. If we tried to count a little bit further out, we could go 1, 2, 3, 4 bonds. We're at a hydrogen, but we're now outside of that 3 bond limit. We can't count that hydrogen as a neighbor. Most of the time. Okay?
No disclaimers.
So in the case of our red hydrogen, we only have those 2 neighbors. What happens with our blue hydrogen? I changed my mind. That one's going to be more difficult. Let's look at our orange. They're all going to be more difficult. So take a look at our blue hydrogen. How many neighbors do they have? The blue hydrogen, we've got 1, 2, 3, ended at a hydrogen. We could count out another 3, and we'd end at another hydrogen. Do those 2 count each as a neighbor?
Yes.
Why do they both count as a neighbor? They're both chemically the same. Why would they count differently?
Different chemicals within the blue hydrogen.
They're different from the blue hydrogen. That's ultimately all we care about. Okay? Which means that we're also going to see that other red hydrogen count as a neighbor. The analogy that I like to use in this case is that if you look at your neighbors, okay, the house next to you or the apartment next to you, assuming there's not just one person living there, there's a couple people living there, you're going to have a different interaction with each of those people, even though they're all considered your neighbors. Okay, that different interaction is what's generated in our multiplicity. So in that direction, we have 3 hydrogen neighbors. But is that it? We could also have gone the other direction. So 1, 2, 3. 1, 2, 3, and another hydrogen. All of those hydrogens are now neighbors. So to the simplest level, we could now say we have how many neighbors? 5 neighbors plus 1, we get 6 peaks. I'll attempt to draw this. Taller, 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 or not taller, same height. There we go. 2, 4, 6. That's this pattern that we would expect to come out of it. Okay. Are the green and the purple different hydrogen neighbors than the red? Yes. Depending on how different they are, we can't count them all as the same type of neighbors. Okay, so let's run through, let's say that again. Our red hydrogens are different from our green and purple hydrogens. When we look at splitting, it's only based on a particular type of neighbors. If our red and our green and purple are different enough, we cannot count them or group them as one set of neighbors. We have to count them as 2 sets of neighbors. Okay? Any ideas why that's important? It's going to change the peak splitting. The peak splitting is due to neighbors. So how is it going to change the peak splitting? So I'm going to need some more space to draw this. So I'm going to have to erase all that stuff above it.
So the blue hydrogen would essentially have 5 neighbors?
So our blue hydrogen, and what we're going to run is 2 sets of neighbors. We're going to call it, okay, our 3 hydrogen neighbors, and we'll call it our 2 hydrogen neighbors. Our blue hydrogen sees the 3 hydrogen neighbors. Let's say it sees them first. What happens? What happens to the signal for blue? Splits into 4 peaks because it has those 3 hydrogen neighbors. So what we would expect to see would be 4 peaks. But wait. We have those purple hydrogens, which are also neighbors. Okay? And if we push this to the limit of saying that those are significantly different neighbors, we now have to have them split that signal. What does that mean? Instead of it being 4 neighbors, or 4 peaks, what I'm going to get is 4 peaks, and each of those peaks must be split into 3 peaks. Why 3 peaks? There's 2 hydrogen neighbors. So what ends up happening to our data? What we'll end up seeing is something along these lines. Okay. What ends up showing up in the spectrum would be this. However, how different are those situations? Not all that different. So what ends up happening is that those signals start to overlap with each other, and the net result, we just see that. Okay, we end up just seeing our 4 peaks because those chemical shifts aren't different enough to completely separate, and they stack on top, and we end up seeing the overall initial or 4-peak situation. Sorry, 6 peaks, yeah, we won't see the 4-peak. Okay? So the purple signal stacks to get us to the position where we actually have 6 peaks because we had 5 total neighbors. Okay, so our purple signal starts to overlap outwards, and we end up getting our end result. This is known as splitting of splitting. Everybody loves splitting of splitting, right? Okay. Big complex mess. Okay. What's going to make this even worse? Was it really just 2 hydrogens? No, it was actually 1 green hydrogen, 1 purple hydrogen. So it's not just a 3 hydrogen split followed by a 2 hydrogen split. It's a 3 hydrogen split followed by a 1 hydrogen split followed by another 1 hydrogen split. And we get splitting of splitting of splitting. Okay. This could go on forever as far as we're concerned. Do we have to worry about it? Probably not, because our instruments are not big enough to be able to detect the difference between those splitting patterns, and usually what we can get away with is just counting the total hydrogens as our neighbors and just looking at that signal. Where it becomes problematic is if we have drastic differences on those sides, right? If our neighbors become drastically different. The way to make them drastically different, attach them to crazy functional groups. Instead of that being a methyl out there, we turned it into a chlorine or 2 chlorines. Okay? That's going to now drastically change the overall structure, and what ends up happening is we get this complex splitting of splitting situation. Okay? So that's what's happening. Oh, I even drew it up there. Okay, that's what we've got in this case. Okay, our splitting of splitting. Thankfully, we won't have to see this too much. If you try and do the really difficult questions within that spectol file that are listed there, 4, 5, 6, and technically A, yeah, I think all of those give you splitting of splitting issues. Okay. To make it a little bit worse, not only is it just splitting of splitting, particularly when you take a look at A, you will see splitting of splitting, but it's not just standard splitting of splitting. It's also splitting of what's known as long distance splitting. How do we get long distance splitting? Well, what happens is we're looking at hydrogen neighbors, and we said 3 bonds gets our hydrogens close enough to each other to make that interaction. Okay, so if we put on our carbon, those hydrogens could potentially count as neighbors of each other. Let's go through and add colors and just make sure no one tells me they're the same. They're not different. Okay. If I went through and now put on a double bond to another carbon, let's go blue. Can the red hydrogen see the blue hydrogen? Well, in our standard rule set, we'd count out our bonds. Hydrogen to carbon 1, carbon to carbon 2, carbon double bond to carbon 3. We're not at a hydrogen. We'd have to go 1 more to get to the blue hydrogen, which is in excess of our 3-bond rule, which means we see no splitting. Okay? The blue and the red are not neighbors to each other. If everything works out perfectly, though, what ends up happening is that blue hydrogen does get close enough to the red hydrogen to cause splitting. Why would it get closer? The double bond is shorter than a sigma bond, and that can draw those hydrogen atoms close enough to each other that they can see each other well enough to cause a split. It is a secondary splitting effect. You can pull a lot of extra information out of that secondary splitting effect. We will talk about it eventually when we look at alkene functional groups, and in particular how we would evaluate them in the NMR. Okay. Until we get to that point, though, you don't have to stress as much about it. Realize that it will show up eventually, but you're not responsible for it yet. Okay? At this point, I don't have any more slides. Okay, so we can do all sorts of different things here. We can run questions based on what you guys have. UCLA put up this site known as Web Spectra, and I've got that already linked up on the computer, and we can pull up a couple example spectra and start to solve and put them together. And I also have sapling signed up on the computer already as well, so we can pull that up so you guys can see that. The one issue with that is I'm going to have to stop recording because I can't show both of those. Okay? So, what do you